6 pulse rectifier. So, these are the various classification of these controlled rectifiers. Now, single phase half wave controlled rectifier. This is the first rectifier which we will discuss. This comes under the types of control rectifier. Single phase half wave means here the rectification is done either in the positive half cycle or negative half cycle, and further it is a single phase. So, in the upcoming diagram or in the showing following circuit diagram, the SCR connected in line only allows the positive half cycle and blocks the negative half cycle. And the circuit diagram which is coming further, we will see we are employing an SCR as we have positive half cycle of AC signal, SCR will conduct and it will provide the rectified output, but during the negative input half cycle it will not conduct. So, we are getting the rectified output which is half wave, because rectification is done only the either the positive or either the negative half cycle of the AC input signal. Further, the conduction period of SCR can be controlled by changing the firing angle through the gate triggering pulse. Means the what is the meaning of firing angle? Firing angle is the instant at which your SCR is turned on, and this instant is controlled by the gate triggering pulse. So, the output available is half wave rectified DC, which can be controlled by varying the firing angle of SCR. So, we are getting half wave because your SCR is conducting only for the positive half cycle, and further we are having this output for the positive half cycle, which is controlled by varying the firing angle, and this firing angle is further controlled by the gate triggering pulse. Besides this, we are having SCR, and when we are having load, we are sometimes we use freewheeling diode. The function of these freewheeling diode, which is connected with parallel combination with your load, is to provide or is to give low resistance path to the current due to stored energy in the inductive load. We will see this single phase half wave control rectifier, we are employing a load on through a load across which we are getting the DC output. This load can be resistive, purely resistive load, or this can be purely inductive load. Okay? These are the characteristics of the load. So, when we are connecting this freewheeling diode across the or in the parallel combination of the load, first thing it provides low resistance path to the current, and this current is flowed due to the stored energy in the inductive load. Second thing, this freewheeling diodes helps in the commutation of SCR. So, that is why we are using this freewheeling diode. We can call this freewheeling diode as a flywheeling diode or commutating diode, because it helps in making SCR in off condition during the conduction to non-conducting state. So, here again we had discussed that we can have two types of load, that is for resistive load and we can have inductive load also. But for, in resistive load, in case of when load is purely resistive, your voltage and current both are in phase. Current is flowing through the load is in phase between the with the applied voltage. Okay, means you can say the voltage and current waveforms are in phase for resistive load, and in case of inductive load your current waveform is lagging behind the voltage by some angle. So, these are the phasors, you can say phasor diagrams of resistive or inductive load. In case of resistive load your current and voltage both are in phase, but in case of your inductive load your current waveform or your current waveform, your phasor, you can say it is lagging behind the voltage phasor. So, this is the circuit diagram of single phase half wave control rectifier. In this we have input AC source which is shown as VAN, which is equals to under root 2 V sin omega t, and it is providing current Is. After that we are having SCR, which is again 3 terminal device. VAK is the voltage across the SCR, and IO is the current flowing through the SCR, and we are having resistance R, and we are getting V out across this, or output voltage across this R. If we use freewheeling diode, we connect that freewheeling diode in the parallel combination with the load R, and in the next we have the waveform from 0 to alpha. Our input AC signal, in the next we can say our input AC signal is from 0 to pi, then pi to 360 degree, that is the input voltage. But if we see the output waveform, in output waveform from 0 to alpha, at that instant your SCR is in off condition, but at alpha, which is we can say the firing angle, your SCR is turning on, and we are getting output from alpha to pi. Then next output we can say we are getting from pi plus alpha to next interval. So, this is how we are getting the input and output waveforms. Above one is the input, and below the waveform which is shown below, that is the output waveform, output DC rectified, DC output waveform. And further you can see that in case of it is a half wave rectification, and further in case of positive half cycle we are controlling the output. We are having the output only for alpha to pi instant. From 0 to alpha we are not getting any output because our SCR is in off condition, and from alpha to pi it is in on condition, and we are getting output only during that instant. Then this is the load current showing the conduction time and angle, and these are the expressions for the average current in the circuit, which is 1 upon 2 pi from alpha to pi Vp R load sin omega t d omega t. Then from by taking the integration, the final expression will be Vp upon 2 pi RL 1 plus cos alpha. Then we can say the direct current of source current introduced into the circuit by the asymmetrical waveform of this controller has a disadvantage, and that the AC source must be ideal, and this renders the circuit impractical for the most of the purposes. Then we have next category, that is single phase full wave controlled rectifier. Here we are having rectification for the full wave. In the previous we are having rectification for the half wave. Here we are discussing full wave controlled rectifiers. In full wave control rectifiers we have two combination, that is center tapped and bridge. So, first of all we are discussing the center tap. A center tap is a connection made to a point halfway along a winding of a transformer or a inductor, or along the elements of a resistor or a potentiometer. And taps are sometimes used on inductors for the coupling of signals, and may not be necessarily be at the halfway point, but rather closer to the one end. Then the circuit of an SCR as a full wave center tap rectifier is shown in the following diagram. Just as a half wave rectification, SCR can also be employed for the full wave rectifier, but instead of using diodes in this circuit we are using only the SCRs, and RL is the load across which we are getting the DC output, and the both gates of SCRs are controlled by different sources, and by changing the resistances connected to these gate terminals R1 and R2 we are controlling the gate current, or further we can say we can change the firing angle, or we can have controlled DC output. Then the direct component of the source current is eliminated by means of bridge. In the previous we had discussed the one disadvantage of DC component in the supply voltage. So, that disadvantage can be eliminated over here if we are using only the bridge circuit. In that we have a pair of thyristors conducting during each half cycle, and we are giving full wave rectification, and a source current with alternating symmetry. The source current has no direct component, and consequently a non-ideal source such as transformer may be employed. There are now two pulses of load current per cycle of the voltage, and this circuit may be classified as single phase full wave controlled or two pulse. We can say it is a two pulse control rectifier, one and the same thing. Then the DC component of the source current may also be eliminated by employing a transformer. In case of center tapped, we are in the initial stage of center tapped full wave rectifier, we are using transformer. So, by use of transformer, we can eliminate DC component, which is a disadvantage in half wave rectifier, where we are simply employing an SCR, and we are having only load resistance and simple input AC source. Over there, we have disadvantage of DC component, which can eliminate over here by use of transformer with center tap secondary winding. In effect, the transformer has the function of transforming the source from a single phase to two phase source. So, strictly speaking, it is a two phase half wave control rectifier circuit, and the time variation of load current obtained with this circuit is same as in the waveform of source current. So, thus this is a two pulse rectifier. However, since the ultimately voltage source in fact only single phase, this converter is also commonly known as single phase full wave control rectifier. This is circuit of center tapped. Here we have AC source, primary winding N1 and N2 is the secondary winding. We have two thyristors and we have center tapped configuration. So, during positive half cycle, one SCR1 is Q1 is on and Q2 will be off, and during negative half cycle Q2 is on and Q1 will off. So, this is how we are getting rectification during in both positive and negative half cycle of AC input supply. This is the another diagram. Then next configuration is single phase full wave with semi controlled bridge rectifier. The previous one is center tapped. Now we are discussing the bridge rectifier, and it is semi controlled. Semi controlled means here we are using again diodes and thyristors. So, it is called semi controlled. Due to the presence of diodes and freewheeling operation take place without allowing the bridge output voltage to become negative, in semi control rectifier, control is affected only for positive output voltage and it is not affected with the negative. This is the circuit diagram for semi controlled bridge rectifier. Here we have two thyristors and two diodes in bridge configuration. During positive half cycle, S1 and D3 will conduct, and during negative half cycle, S2 and D4 will conduct. So, this is how we are getting rectification for the full wave. And this is the another configuration. In the previous connection, we are having two SCRs in parallel. It can be connected as S1, S2, D3, D4. So, again the principle is the same. During positive half cycle, S1 and D3 will conduct, and during the negative half cycle of AC voltage, S2 and D4 will conduct. And further, the conduction is depend on the firing angle of during positive half cycle. It will depend on the firing angle of S1, and during negative half cycle it will depend on the S2. This is the another configuration. Here it is full wave, where we have 4 SCRs and 1 diode. This is the output waveform, current waveform, freewheeling diode, and these are the mathematical expressions for average voltage, RMS value and for ripple factor. Then fully controlled. In case of fully controlled, we are not using any kind of diode. The whole circuit comprises of only SCRs. So, that is why it is called fully controlled. Like this is the example in which we have S1, S4, S3 and S2. We are having the principle is the same for the conduction, which we have already discussed, and these are the performance parameters. Further, the applications of control rectifiers. The applications of control rectifiers in case of DC speed control system, it is widely used in steel mills, paper mills, and in electrochemical and electrometrological processes, in magnet power supplies, or in converters at the input end of DC transmission lines, or in portable hand tool drives where we can use. And last one is the these are the some pictures of the controlled rectifiers, how it look like. That practically we have seen that the SCR is look like this way and this. So, up till here we have discussed the control rectifiers in various configurations, right. We have discussed the controlled rectifiers and controlled uncontrolled rectifiers concept, their differences, and why we are calling control rectifier as control rectifiers. Then after that we have various classifications of rectifiers. Basis on that we have single phase, half wave control rectifier, single phase, full wave control rectifier. In full wave control rectifier we have center tapped and bridge configurations, and by employing these configuration we have semi controlled and fully controlled control rectifiers. So, this is how we can classify the control rectifiers, and further once we will take up the all these are the applications and these are the performance parameters. In the performance parameters we can say the performance parameters describe that how can we select a particular device for a particular application, like a crust factor which we can compute to facilitate the selection of proper SCR. Then the distortion factor, total harmonic THD, that is total harmonic distortion factor, because in case of rectifiers we have ripples in the output. So, total harmonic distortion factor is very important while selecting a control rectifier for a particular application. So, THD is another performance criteria for deciding to which one is to be select. Then in another performance factors we can say that the role of rectifier circuit is to produce DC output voltage from AC, and the rectifier output is not pure DC, it contains some ripple superimposed on DC current. So, the current drawn from the AC source is not sinusoidal either. The main requirement is that in performance criteria your ripple factor which we are calculating, that should be very low, that should be minimum. So, this is all about the performance and application. Thank you.